This video is to address hypothesis testing, and in particular the hypotheses in a hypothesis test. In a hypothesis test, we are going to be testing a claim about population with respect to sample data, or dependent upon sample data that has been collected. So we want to either refute what has been claimed in the past in favor of new information, or we want to uphold the past information as still being relevant. So this is what we need. We need a null hypothesis, an H sub O, or we need an alternative hypothesis, an H sub A, or sometimes called an H sub 1. Now the null hypothesis always contains equality, and Bioga will only use the equality sign here. You've seen down here in these null hypotheses, that's the notation I've used, but some material will use the opposite inequality. So if it's a greater than in the alternative, then it's a less than or equal to over here. Now, the notation on the alternative or the research hypothesis does vary. It can be H sub A or H sub O. Now, the order that you place these in is totally up to you. A lot of people will put H sub A first because that is the one that's usually taken into account first. You find your claim, and usually it is your claim that becomes the alternative hypothesis. The exception to that rule is that the claim cannot have an equality to be in the alternative hypothesis. So if the claim has equality, can't be the alternative hypothesis. But hopefully it will not contain that equality. So let's go ahead and take a look at the three types of hypotheses. Now what we're doing here, so we have three different sets of hypotheses, and I'm going to take the first one, where our research claim, our alternative hypothesis, is that we are looking at a mean or a proportion. Those are the two types of hypotheses we'll be dealing with. So I'm going to start with just mean notation, is greater than, and this will be some numeric value that's given, and that is assumed to be our population information. So this is our first type of claim. Now this generates what we call a right tail test. What we're looking at here is that our information, if it falls within the upper tail, the mean is greater than some population value, that this upper tail area will mean that this is an unusual value under the claim distribution. Now the claim distribution is what we have for the null hypothesis. So the claimed distribution that we're trying to say it's unusual for is under the alternative, or excuse me, under the null hypothesis. And that would be that the mu is equal to whatever that number is from the population. So this upper tail that's told to us by the alternative hypothesis becomes what we call a rejection region or a critical region based upon the fact that if our test statistic is in this region, or if the probability for our test statistic is smaller than the critical region's probability, then we will reject the null, reject this distribution in favor of our new distribution. So this is called a rejection or a critical region. And that is how a hypothesis test is conducted. So you remember back in the time period where we're talking about the empirical rule, and we kind of came up with these ideas of being unusual or very unusual, hence outliers, based upon probability, based upon number of standard deviations away from the mean. Well, that's basically what a hypothesis test is doing. It's saying, okay, well, I have this value for the sample, and I'm holding it up. I'm going to find against this null hypothesis underneath this distribution, where does it lie with respect to other values from that distribution? And if it's in what we've set up as being the unusual region, then it's not likely that it belongs to this null hypothesis distribution, and so we'll reject this distribution in favor of our claimed distribution. And it's because of the claim that we do set up where this rejection region is. And you're going to see as we go through the three different types of tests over here, the one-tail upper tail test, the one-tail lower tail test, and the two-tail test, that it is those this alternative that sets up this rejection region. So now let's go on to the lower tail test. So this lower tail test, we have our alternative or our claimed hypothesis being that mu is less than some number from the population. And this one, we're going to set this up as being a rejection region in the lower area. So this is our rejection region, RRR is what I'm going to call that. And this is a lower tail test. And the lower tail test is going to be based upon the value of our test statistic under the null hypothesis. And by the way, the null hypothesis won't be any different than it was before. It looks like mu is equal to this number. And that if underneath this hypothesis, our test statistic, which is just a z-value by the way, is down in this rejection region, then it's unusual for this null hypothesis and we'll accept the claim here. So what we're going to look at finally is for a two-tail test. And for a two-tail test, our claim is that it's just different. So different could be big or small. So when we say it could be big or small, it could be different than some number. What we're doing is a two-tail test. So this could be too big or it could be too small for the claimed distribution of equaling this value. But it's different. So this different gives us what we call a two-tail test. And in a two-tail test, there is a rejection region down below as well as a rejection region up above. It's in two tails. So now what I'd like to do is I'd like to go through and I'd like to show some examples of a one lower tail test, upper tail test, and of the two-tail test, and show you how you pick out the information that's needed to write these hypotheses. So let's start with example number 1 here, and let's write this example out. We'll be looking at the null hypothesis and the alternative, so I'll write the HA there first and then the HO down here. And what we're also going to be careful of is whether we're dealing with proportions or whether we're dealing with means, so that we get the correct population parameter in here when we write these out. So this one says a manufacturer of new medication is testing it against an old medication that has a success rate of 60%. Well, first off, a success rate of 60%. That's telling me that this is proportions. So I have a parameter of a p, and that p is in both the null and the alternative. Now my null hypothesis, remember, has equality in it. So the manufacturer will not accept the new medication unless it has a success rate better than the old. Better than the old is very important here. Better than the old is what the claim is. So better than the old means greater than. And what is the old success rate? Well, the old success rate's right there, and that old success rate is 60%. So we're going to put in 60%, or you could put in 0.6 here as well. So 60% is what we have for a success rate there. Now this, remember, tells us that this is going to be an upper tail test, and this is going to be my rejection region up here. So this is where we're going to set this test up. Okay, now this information goes on and tells you the information of how to do this. So eventually I can come back to this little handout here and I can show you actually how to conduct these tests. But right now we're just setting up these hypotheses. Now, number 2, the administrator of a nursing home would like to do a time in motion study of staff time spent per day performing non-emergency type chores. In particular, she would like to test to see if efficiency is up. Now, mind you, efficiency is up means spending less time on chores. Spending less time on chores, that is going to be our alternative hypothesis. And what we're looking at is time. Well, time is a quantitative piece of data, right? So this is talking about mu's. Now, both my null and my alternative have mu in them, don't they? So they both get mu's. Remember, the null hypothesis always has equality. And now I need to put in less than here, right? So the less than. So I'll go over here and put less than. So that makes this a one-tail, lower tail test. So here's my rejection region over here. And the next thing that I do is I need to find out what number is it being held up against. So we want to see if efficiency is up from a prior study that showed an average of 16 hours. Now you see this name right here, average, right? That's another indication that we have a mean. So 16 hours is the number that goes in here. Doesn't matter if you put it here or here because it goes in both of them, right? Because that's the breaking point. All right, finally, let's go down and let's look at number 3 here. And number 3 says, in a sample of 40 company cars, the average miles driven was 2,752, with a standard deviation of 350. At 95% confidence level, test the claim. So here's the claim. Last year's average was not the same, this year's average. Sorry, I think that should say this year's average. Is not the same as last year's average. So last year's average was this, right? That's what it's being held up against. And so not the same. So first of all, when we're doing these hypotheses, right, what we need to decide on is, first of all, what is the population parameter that we're looking at? This word average, that tells me, plus the fact that miles driven is a quantitative piece of data, that these are means. So I'm going to put in means. And so I know equals to, and the claim, not the same. Well, if it's not the same, it's not equal to. And then last year's average, which is being held up as the population, right? That's what we're comparing against with our sample, is 2,600. And that 2,600 miles goes both there and there. And now we're done. And this, of course, is a two-tail test. We have a lower rejection region and an upper rejection region because we're not sure which one it could be, upper or lower tail, right? But it is one or the other. So that is how we do hypotheses. Now, my next video will probably be talking about what do we do with these rejection regions and how do we actually conduct the tests.